I'm going to talk a little bit about the history of RISC-V at NVIDIA, and it reminded me, I talked 7 years ago in 2017. I gave a keynote at the 6th RISC-V work group, which was held in Shanghai. We hosted that together with Jiao Tong University. First time that I think there was any official RISC-V activity in China, so it's, things have come a long way. And at that time I talked about our internal microprocessor Falcon that we were planning to replace by RISC-V. And 7 years later I'm going to talk about what happened actually, and it's amazing how close things followed the plan at that time. So Falcon was our internal microprocessor. We had used it for about 10 years, and we decided to replace it by RISC-V. We did a analysis of what architectures would be good. We decided on RISC-V. And since then, we have been adding more microcontrollers to our chips, and also we've been slowly replacing all of the old Falcons, which have had a long tail. At that time I told the audience that we had about 3 billion Falcons shipped in 10 years, and I said, well, we think we're going to have billions of RISC-V processors. Now I can say that has come true. I did a quick calculation for 2024. We have any NVIDIA chip has RISC-V processors, and I would say it goes from 10 RISC-V processors to about 30, maybe even 40 RISC-V processors per chip. You know how many chips we sell roughly, right? You can find that on the internet. And so if I multiply that, I know that we sell, and I said here, about 1 billion RISC-V cores in 2024. I think that's a conservative estimate. It's somewhere between 1 and 2 billion RISC-V cores that we ship this year. We've been a member since early on. Callista just said it. I was a member of the inaugural board, right? That's like, besides me, Kirsty is still there. Other than that, all board members are new, so I'm one of the old guys. I don't have a perfect record because I was not on the board for about a year, but most of the time I was there. We're also part of RISC, which is the software equivalent that we have, and we contribute to many of the technical work groups. Specifically, we like to contribute if we do something ourselves or it makes sense to us, right? And then we want to make a change to the architecture or add something to the architecture, right? That's where we contribute. We also use a lot of the results of the community, compilers, simulators, etc. One of our partners, Ada Core, we use the Ada Spark extensively, and we work with them for safety certification. So we're part of the community. You don't hear it that much, right? So most people, if they think RISC-V, they don't think NVIDIA, or if you think NVIDIA, you don't think RISC-V. And that's because most of our designs are done in-house. Our software is developed in-house. It's not customer-facing. But it doesn't mean it's not important. It's actually very important to us. I talked about applications. We have 3 uses for RISC-V. Function level control, right? So video codecs, for example. Every video decoder that we ship has a RISC-V, right? And display, camera, a lot of those kind of function level controls. Then at the chip level, we have 3 main functions that we use RISC-V for. Resource management, I'm going to talk about that one later. Power management, and security. Security, you'll see also a lot in my talk. Recently, we've also started using RISC-V for more data processing functions. One of them, the DL network layers, I'm going to talk about later. The other one, I feel very sorry I can't talk about it later just because I don't have time, but I'm going to say something about it now. Our network business unit, NBU, actually does a lot of packet routing in RISC-V, right? And that's the RISC-V that they use is a 16-core, 256 hearts RISC-V. It's a very interesting design, and they go full speed packet processing through that, right? So every packet goes through it. So I've said something about it. Our RISC-V cores, we started with a RISC-V 64 bits. That was one of the main reasons why we switched away from Falcon, is that we didn't have 64-bit address spaces, right? Falcon was a 32-bit core. We needed 64. So we have I would say, fairly standard 64-bit RISC-V processor with the kind of extensions that you might expect. It's a dual issue out of order. We do have ideas that maybe we go to 3 issues at some point, but for now we have sufficient performance there. We also allow multiprocessor versions of this. And more recently we developed a 32-bit version, right, which is mostly area constrained. And we have a vector processor with a 1024-bit vector unit attached. We also have a lot of our own extensions, which are extremely important to us. They're not useful for everybody. Some of them are, some of them are not. I'll talk about a few. The 2 kilobyte page sizes, for example, shows you that we have a lot of old software. And with that old software, if we run it, we can get a 50% performance improvement by using 2 kilobyte pages. It may not be something that we say, hey, we want to push that into the standard because it's just not useful for everybody, but it's very useful for us. And then we got the 64-bit addresses that we use. Some of that is because we have very big systems and we like to address those very big systems. For example, in a data center, right, you have a very distributed memory. It's not just one main memory, but the memory is everywhere, and we like to address those memories that are far away, so extra bits are helpful there. The other things is, for example, pointer masking, right, which is good for security or safety, right? And that is something that many people use, and the pointer masking standard has just been approved. We had it way before it was approved, and we actually helped to bring that into the RISC-V standards, right? So it's a new extension that just got approved. In general, functionality, security, and performance are the 3 things that we have our own extensions for. None of these extensions is like mind-boggling or very high-tech or something like that, but they're very important for our system. Then reuse, so we actually have a bigger subsystem that we call Peregrine, which other than just the RISC-V core also has a bunch of peripherals for example, DMA, for security. It has the tightly coupled memories with it, right? And why it's important is because it's a single system, and we have, as I showed, we have about 30 applications, and we do not want to develop each of these applications independently, right? So what we do is we pick and choose here from this subsystem, right? This subsystem is one single architecture. You can choose which RISC-V extensions do you want. Do you want the 32-bit? Do you want the 64-bit? How much memory do you want? How much security do you need? right? All of these things are configurable, so we get a lot of reuse by doing that based on this bigger subsystem. Switching to the software side, again, reuse is the big thing here. We have one single software stack that we use over all our applications, all our 30 applications. All the green parts that you see here in this slide are reusable, right? Which includes the boot, the OS, the separation kernel. I'll talk about a little bit more, and then there's a lot of libraries that are being used, reused in the application level. Again, a lot of configurability, reuse. On the security side, as I said, is very important to us. So we have, we program a lot in Spark, Ada Spark. We also have our own OffSec team, offensive security team or something like that. That's what it stands for. And they are basically trying to break our designs, right? And they try to find the bugs, right? And they're kind of our own version of the hackers. And we try to keep things secure. So security is a key for us. A little bit more about the separation kernel. So separation kernel was, I think, introduced by RISC-V in 1981. It's a very, you can think about it as a very bare minimum hypervisor system, right? It divides the system into different pieces, and those pieces are independent of each other, right? And they can be independently verified, and it's the separation kernel makes sure that there is no interference between them, right? So in one core, you could, for example, run a piece of software that is secure or has a safety requirement, like ASIC-B or ASIC-D, together with software that is does not have that kind of requirements, right, and does not go through those certifications. So that's another part of our software stack that's very important to us. Yeah. Now I'll talk about a few applications. The first one I want to talk about is our GPU system processor, or GSP for short. It's probably the application that has led to the most fundamental changes in the way that we do our software. So the GSP is a processor that sits basically, I would say, at the top of the GPU, meaning all the traffic to the GPU comes into the GSP. And it basically creates an abstraction of what you can do in the GPU, right? So rather than the host processor and the kernel driver banging on individual registers, control registers inside the GPU, they just talk to the GPU, to our GSP, and the GSP translates those higher level commands into lower level, say, control register writes. Looking a little bit at what it is, it's basically a 64-bit RISC-V architecture. It's multi-hard, potentially, right? We have different versions. We have single core and multi-core implementations of it. The other most important thing of it, of course, it has full access to everything in the GPU, including also access to the memory controllers, the display controllers, right, which are some of the things that you really need to manage very carefully in the software. And if I look at it from a software perspective, we could have a host processor that has a kernel driver and a number of guest virtual machines, right? So, for example, here, this what I'm showing is a GPU that is in the cloud, right? It's there's multiple guests that are running on the GPU. The guest virtual machines do not have to talk really to the hypervisor. Everything happens really on the GPU via the vGPU runtime software that we have running over there. The separation kernel makes sure that the different guests are not interfering with each other, right? So they're completely isolated of each other. They're also isolated of anybody that runs the server in the cloud, right? So it's a complete isolated environment where quality of service is guaranteed by the resource manager, right? The resource manager swaps in and out different guest software and make sure everybody gets their fair share. This also allows us to do, for example, confidential computing, right? Where the GPU is handed over to a guest without the hypervisor having any impact on that. So and RISC-V here is foundational because of its security and isolation capabilities, and our custom extensions basically make this even stronger. The other application I want to talk about is it's where, after all, NVIDIA, so we do AI. We do RISC-V. RISC-V is not really part of the bigger GPU AI, but we have what is called DLA, Deep Learning Accelerator, which is a part of some of our SoCs. And it's basically an inferencing engine. That inferencing engine is basically programmed in a graph processing way, right? So you could, for example, write an ONNX program that represents a graph of layers, right? That are being processed in the deep learning network. We then have the more or less standard RISC-V compilers that take these kernels and turn them into an executable. And on top of that, we have an RISC-V compiler which turns it into a loadable. We also have the opportunity to combine different kernels at the graph into a single kernel for runtime, right? Basically, for example, think about a convolutional core followed by a nonlinear function, right? So you want to combine those for the fastest execution. DLA, it's not running as everything on the RISC-V processor. The main convolutional cores, the matrix multiplies, are a separate entity, right? So if you look at the hardware picture on the left, there's actually two RISC-V here. One is for the control, which is a simple 32-bit RISC-V. And then there's the vector unit, which is the RISC-V, is a 1024-bit vector unit. We also have, so we have the convolutional core. We have overall 6 hardware engines. For example, Rubik is kind of doing all kind of data transformations, basically shuffling data around. But the RISC-V, the RISC-V vector processor, is used for most of the layers that are not the matrix multiplies. So think about softmax, all kind of nonlinear activation functions, right? We basically have a full ONNX implementation running on this DLA, and most of the layers, as I said, are done by the vector RISC-V. So those are just 2 of the applications that we use. So looking back, and this is my last slide, I got 20 seconds, wow, very good. Looking back at it, what has, I think, led to the success, and why did we choose RISC-V, and why is it successful? I think customization is really the key here. With Moore's law ending, right, using every bit of your silicon for that is necessary, for good use, right, is key, right? So customization becomes key, and the licensing model of RISC-V, right, where you're basically free to do things that you want. The fact that it's built with extensions, so the ISA is basically built as a building block in a building block way. Profiles, we use profiles, internal profiles, right? As I said, we got a lot of options, but we use the idea of a profile saying, hey, we don't want every core to be different, right? So we take that idea as well in our own internal development. So hardware, software co-design, I think both Calista and Xiaoning talked about it, right? We see the same thing. Hardware, software co-design is key. The fact that we can configure, we pay only what we need. The fact that we can add our own custom extensions are all really key features of RISC-V that we used. As you could also see, customization could lead to divergence and a lot of extra work, right? So we, as I hope I showed, we had one architecture, right, that we use for everything. So even though we have a lot of different versions of RISC-V, a lot of different pieces of firmware, all of it is based on a single architecture. So my title was One Architecture, Dozens of Applications, Billions of Cores. I think it's good as a title, but actually I worked the other way around. I told you first we do 1 billion cores this time around. I showed you some of the 30 applications that we actually use, and it's one architecture, one hardware architecture, one software architecture that it's based on. That's it. Thank you.